Hello.
Hi.
Yeah, can you hear us?
I can hear you.
Yeah, okay. Okay. So welcome everyone to the online session of today. We have Dries from New York University and Flatiron, who will be talking about quantum chaos and the effects on MBL.
Yeah, thanks for the introduction and thanks for the invitation to give this talk. Yeah, let me start by apologizing for not being there in person. To be clear, I had all my flights and travel arranged, but there were some visa issues. So at the end, I had to cancel. Um, Yeah, and normally I'm never this early in my office, but it turns out because my window in my office is facing east, that the view is kind of spectacular early in the morning. So I took a picture just 2 minutes ago so I can share it. So that's what New York looks like at 7 a.m. So with this, let's sort of get started. And in the next, let's say, half hour or so, I'm gonna try to give an overview of some of the things we've learned in the past couple of years on MBL. Given the topic of this workshop, I think that's sort of pertinent. And um, obviously, in a 40-minute talk, I will not be able to explain all the details of all the things that we've done, but I hope some sort of coherent picture will emerge from these studies that we've been doing. And well, since I don't exactly know who all is in the audience, I assume a lot of experts, but maybe also some junior people. And since this is recorded, I'm going to try to give a very, very brief but somewhat self-contained introduction to the problem. So, okay, so again, probably this doesn't really need a lot of introduction, but the problem I will be talking about looks somewhat like the following. So in the 50s, Anderson had one of these seminal papers in which he showed that in certain random lattices, there is no diffusion, by which formally means that effectively the approximation that it does, even though it doesn't call it that way in this paper, is some non-interacting particles that can hop, and there is some disorder potential. So this might look like this. You have some sites. These sites can be empty or occupied, and there's some disorder. So these energies are disordered, and you can have some hopping between those sites. And if you have a local Hamiltonian, then Anderson sort of showed, and this is by now also very rigorously proven, that above a certain critical disorder, there is localization, meaning the single particle wave functions are exponentially localized. And this happens in any dimension above some critical value of the disorder. But of course, the more interesting question is basically this question of many body localization, that is, what happens when we add interactions to this problem. So we're going to add some interactions U to this problem and sort of ask, is this localized phase stable? Meaning, if we have interactions, how does this change the picture of Anderson localization? Can we still get localized orbitals, or is something else happening? And so, okay, since the 50s, there's been a lot of work. The first work on this was obviously not the BAA paper, but okay, let me list in at least the current sort of revival of this subject was maybe ignited by this paper in 2005 by Pascual, Leiner, and Altschuler, which sort of do a self-consistent Born approximation calculation, which is the leading order diagram, basically, if you do perturbation theory in U, and sort of show that, yes, if you compute the inelastic scattering rate above some critical disorder, below some energy density, so there's a mobility edge, actually, is the conclusion, the inelastic scattering rate tends to zero. And so this was motivation to basically study this problem more rigorously and better and numerically. And well, that's what we all have been doing, I guess, in the past 15 years or so. So I'm not going to describe everything that happened in the past 15 years because I did a small literature sort of survey and made a citation graph. And actually, the field of MBL is, by any standards for condensed matter, gigantic. So there's a lot of things that have been done and a lot of things that have been said. So I'm going to try to colloquially sort of summarize it in the following, which I call the pre-pandemic consensus. That is that in one dimension, so this is one of the conclusions that actually in higher, and I'll come in a second to why we come to that conclusion, but that this stability can only be there in one dimension, and that in one dimension there is an ergodic phase and an MBL phase, and there is a critical point in between with a dynamical exponent that diverges, so Z is infinite. In the ergodic phase, this is characterized by eigenstate thermalization, normal sort of diffusive transport, and if you do a quench from a product state, you'll get linear growth of the entanglement. In contrast, the MBL phase has local integrals of motion. There's no transport because of these local integrals of motion. Because of the fact that there's extensively many local integrals of motion, the system also doesn't thermalize. And sort of the crucial difference with the Anderson insulator is basically that nonetheless, there is logarithmic growth of the entanglement after a quantum quench. And so the rough estimate, and of course, we all know by now, and I assume there have been many talks on this, that the rough estimate for a long time for this critical point was about disorder 3.7, let's say in the XXZ or Heisenberg model, which in my notation here is U is J is 1. Of course, we know that it's larger, and that will be part of my talk, basically. So in order sort of to focus the discussion, and it's really useful to focus on one of the things that sets apart the Anderson insulator very, very clearly from an interacting many-body system. And one of the things that is very easy to understand is basically that in every model that has disorder, there will be rare inclusions. And there are inclusions of any sort of type, but for the current discussion, it's okay to focus on rare regions where the disorder is weak. And so with rare regions where the disorder is weak, I mean consecutive sites in this model where the disorder is smaller than a certain amount. And so if the disorder is small enough, well, then of course, effectively, it's like the disorder is not there. Again, we just said that there should be an ergodic phase in this model too. So as long as in some local region, the disorder is such that locally you would be in that ergodic regime, well, that local patch should basically obey eigenstate thermalization. And the question is, what are the consequences of that? But before we look into the consequences, well, it's good to actually sort of get a rough estimate of the probability that these things will occur, right? And this is really simple. So the probability that L consecutive sites will have a disorder smaller than epsilon, well, roughly goes like epsilon over W to the L, where W is the typical disorder that I will be drawing. So it's exponentially small in L, and the base of this exponential is epsilon over W. Now, if we want this rare region to have any sort of measurable effect at all, well, first of all, since the disorder is weak, the many-body bandwidth of this rare region, well, it's set by the hopping J, and it's just proportional to the number of spins that you have, right? And there are no states outside that energy window, so outside that bandwidth. But the typical energy for a spin in this typical region, well, that's where the disorder is large. That's on the order of W itself. So now, if we want to have any effect, that is, if the first spin in this, say, typical region has even the ability to resonate with any state in this bath, which is sort of the minimal requirement to get any effect at all, well, then there should at least be many body states at the typical energy of W, right? But there are only states in this bandwidth J times L, which basically means that, well, for a rare inclusion to sort of have an effect, you need this rare inclusion to be on the order of W over J, right? Which basically you come to the simple conclusion that the probability that there will be a rare region, one that actually is important, is maybe on the order roughly of J over W to the W over J. And as we all know, the discussion we're going to have is basically about disorders that are on the order of 10J, right? So if we're discussing disorder on the order of 10J, well, then it means the probability, if I just chuck this in here, the probability that just by sampling, I will get a rare region that is relevant, well, the probability of that is 10 to the minus 10, right? So yeah, so that's a very small number. And of course, that's the whole point. I mean, these inclusions are rare. That's the thing. They're exponentially rare. But we all know, and I'll come to that in a second, that they are important, but sort of the somewhat surprising thing is that we've not really, at least on the numerical side, taken into account the effect of these rare regions until pretty recently, I would say. And I mean, there's been a bunch of papers maybe in the past couple of years also sort of claiming that, well, if we had 50 sites or if we had 100 sites or something like this, then definitely with numerics, we would be able to conclusively say something about MBL. But the main point of this slide is to point out that it's not true, right? I mean, you need to go beyond that because the probability of having such a rare region is 10 to the minus 10. So if you want to make sure that this is captured by your numerics, well, you need to sample 10 to the 10 spins, right? So your system size that's required is quickly going to get on the order of Avogadro's number if we even increase the disorder only a little bit, right? And so this is the heart of the problem. But what is the effect of this rare region? And I guess this has also been discussed in this workshop so far, but just quickly to recap for all of those that know. So if we assume that in this typical strong disorder region, we do find exponentially localized Lioms, well, then it basically means that the matrix elements between that can basically flip one of these Lioms because of this rare region, well, these couplings should decay exponentially. And they should decay exponentially with the localization length of these Lioms, which we should be able to tune by making the disorder larger. But now what can happen? Well, if the relaxation rate, which is basically set by this matrix element, obviously is larger than the level spacing of this, let's say, rare region, well, then the relaxation can happen. So then what will we say is that this is the simplest possible sort of model, is that these spins will join the rare region if they can actually relax, and they can relax if they relax faster than the level spacing. And then they will join this rare region. But if they join this rare region, well, then the level spacing decreases even further. So that means even more spins can thermalize and so on and so forth. And so you have the ability to basically thermalize the whole system. However, if the relaxation rate is smaller than the level spacing, then the process must stop because, well, if you compute any sort of relaxation rate, clearly, if you see the discreteness of the spectrum, well, before the relaxation happens, well, then something else happens. You will just basically have Rabi oscillations or resonances between discrete levels. So the process stops. And so that basically, this is the reason why in higher dimensions, we do not believe that MBL can be stable because basically the level spacing of a rare inclusion grows too fast as compared to the decay. But in one dimension, you get two competing exponential processes, exponential growth of density of states, and exponential decay of the coupling. So that means there is a critical psi where basically if the localization length is smaller than this critical length, this avalanche will stop, right? And so this is just basically the idea behind almost all of our understanding by now of MBL, that we should find Lioms that have small enough localization length, and then we can be stable to these avalanches. So the rest of my talk, I will basically therefore focus on trying to find these Lioms, right? Because we need to verify that these Lioms are there. But before I want to do that, I just want to show you some numerics to maybe convince the people that are skeptical of the idea that avalanches are really there. And so in order to do that, we, with one of my students, just did a very simple experiment. And the experiment is just the following, is that, of course, by sampling just unbiased random numbers, we're never gonna be able on a computer to simulate a system that is large enough such that it will contain actual rare regions, right? I just said that the probability is roughly 10 to the minus 10. So this is not going to happen. But of course, no one forbids us to do like biased sampling. And we're all used to doing that, right? I mean, if we have, just to give another example, if we have any sort of event that is rare, let's say we have some first order phase transition or some nucleation event that is exponentially rare in some molecular dynamics problem, well, you can run your molecular dynamics forever. You're never going to observe it because you're looking at trying to find something rare. Instead, what you do is you basically induce the event. So here the philosophy is the same. Of course, we're perfectly allowed to insert by hand a rare region where the disorder is weaker and study the effect. And so in order to study the effect, I'm just showing you here a simple plot where I look at the imbalance, which is we start in a staggered state that is a empty occupied configuration, and then we look at how much memory are we retaining with respect to that configuration for different disorders, and this is all in the Heisenberg model. And so we do this simulation on sort of the largest system we can do. So this is a simulation done, I think, on 26 or something spins in total, and we insert a rare region of 10. Well, this I will do in a second, but if we don't have any rare region, then this is what the numerics looks like. So basically, at disorder 6, actually, even from not doing anything at all, we still see some substantial decay of this imbalance. And even at disorder 8, maybe you could see some small decay, and this is consistent. I think I saw Piotr was on the list of participants. So, I mean, they have also done some numerics in the past couple of years, sort of showing that if you actually simply look at the imbalance, you can already observe that even at these disorders, there is still some decay of this imbalance. But okay, at disorder 10, let's say 12, it's becoming really, at these timescales at least, impossible to see any decay at all. This is in absence of having a rare region. So now I'm just going to sample on the side this region with weaker disorder, and I'm only going to look at the imbalance in the middle of this high disorder region. Because, of course, if I look at the imbalance in the weak disorder region, this is going to decay very quickly, right? That's not the effect that I want to look at. And so if we do this, well, we see a remarkable difference, right? We see that actually at all of these disorders, these rare regions have a drastic effect. They speed up the thermalization by a significant amount. And now the next thing is, of course, you could argue that, well, the larger the disorder is, the smaller the effect seems to be. So maybe we are getting into some sort of many-body localized regime. But you could easily sort of replot this data that is simply, instead of like, we're only doing the following, we're rescaling time. So I'm going to rescale the time by an exponential of the disorder strength and then plot all the curves on top of each other. And I would say that, of course, the data without rare regions, I mean, this is this light data over here. okay, that has some behavior, but the data with the ray region seems to collapse quite nicely to a universal sort of curve, which gives an indication that all that we are observing in this numerics with a rare region is that if the disorder increases, the timescales increase exponentially. And so that means there seems to be a universal relaxation, which is just exponentially suppressed in the disorder strength. And just to be clear, I think also Tomaz and maybe Lev are there. I at least saw their names on the schedule. I mean, this is consistent with observations before that if you look at the spectral form factor, it seems that the tauless time is simply scaling exponentially with disorder, right? And so now that we have this observation, now the question is, well, can we explain this universal relaxation, right? Because it's one thing to observe this, and you see that this observation is consistent with finite size sort of MBL, but it would mean that MBL in the thermodynamic limit is unstable. But the question now is there an explanation for this that is reasonable? Because that would substantiate more that this is really what's going on, and this in and of itself is not just some finite size numerical effect. And so in order to try to understand it, I'm going to do the following thing. I'm going to, instead of really doing numerics and looking at the dynamics, I'm going to replace this bath that I inserted by an infinitely weakly coupled ideal bath. That is, I'm going to make some Markov approximation that this bath is Markovian, so I can replace it by a Lindbladian, but I'm also going to couple it infinitesimally weakly to this MBL region. And then I'm going to ask, what is the relaxation that gets induced when I couple infinitely weakly some bath on the boundary with this MBL region? And okay, for the sort of details on how this can actually be computed, I'm going to refer to my paper, which you can read. But roughly, what it amounts to is basically computing the residual commutator of the best possible integral of motion that you can construct in this finite size MBL system with the boundary. And indeed, you could imagine that if you could commute, if you can construct a Liam that commutes with the boundary, well, then of course it has no chance of relaxing if you couple a bath to it. So the actual relaxation rate is set by the residual commutator, which indeed measures, if you were to write it in some eigenbasis, the matrix elements with respect to this bath coupling. And so the way we're going to try to construct these integrals of motion is in the following, and I've depicted it here. So basically, if we go to infinite disorder, well, then at infinite disorder, I of course know what the integrals of motions are. They're basically just the local sigma z operators in my spin chain. So I know the eigenbasis at infinite disorder. Now I could, let's say, this is not how you do it numerically, but I could at least sort of philosophically transport these eigenstates to weaker disorder. So I just change the disorder, and then I adiabatically follow all these levels. And of course, there's going to be a whole mess of sort of level crossings. But at some point, I get the actual energy eigenstates at finite disorder. And so this process of going from configuration space to going to energy eigenspace, well, it's characterized by basically the matrix elements between the energy eigenlevels at finite disorder and the configurational levels, and they form a double stochastic process. That is the probability to go from configurational state, say Z, to an eigenstate is a double stochastic process Q. And so now you see that, let's say, if there would not have been any level crossings, well, then this double stochastic process would basically be almost a diagonal matrix. Or in other words, if nothing happens, this double stochastic process Q is just a permutation of levels. If there would just be many body resonances and the only thing that would happen is that two energy levels would collide and cross, well, each of those collisions is a permutation of energy levels. And so to find Lioms at the end of the day, the only thing that you have to do is basically try to unravel this kind of scattering process of many body levels. That is, in other words, to find the permutation matrix P that is as close as possible to this double stochastic matrix Q. And okay, you can find the details if you want somewhere else, but it turns out that finding the permutation matrix P that's as close as possible to this double stochastic process Q, that's actually a linear assignment problem, and a linear assignment problem can be solved in polynomial time. So there's actually an efficient algorithm like n-cube algorithm to solve this assignment problem. So in the end, we don't have to do this actual transport problem. We just have to compute the energy eigenstates. We have to express them in the configurational basis, and then we can basically find what is the correct assignment of each many-body interacting level to each non-interacting level. And once we have it, we can easily construct integrals of motion from it. And so that's the procedure basically. But now if we do this procedure that I just described to you in words, and now we look exactly at the residual relaxation rate, if I look at those Lioms and I ask if I were now to infinitely weakly couple a bath on the boundary, how would these Lioms decay? And so here I plot the relaxation rate as a function of distance from the boundary. And the different lines here are just different values of the disorder. And the different colors, sort of shades of blue, they're just finite sizes. I do the numerics in finite sizes and plot all the different finite sizes. So there's a number of observations. That's basically, well, we observe perfect exponential decay, right? Because these lines are perfect straight lines. That's one thing. The second thing is that there's essentially zero finite size effects in this numerics, right? Because whether I do the numerics for 5 spins, 6 spins, 7 spins, 8 spins, those lines, they all coincide. And if I increase the disorder, which is, this is the smallest disorder and the one that decays the fastest is of course the largest, I can just tune the localization length or this exponential decay by changing the disorder. And of course, that's all reasonable because that's what we know from the Anderson model is that basically indeed, we're working here at such large disorder that, of course, we don't expect finite size effects because the localization length is extremely small. So why would the system care about the boundary? And yes, we can tune the disorder. So this all makes sense. And I'm deliberately doing this numerics in exactly the same way I'm going to do it on the XXZ model, even though we can solve it, of course, much better on the Anderson model because it's a single particle problem. But once we go to the Heisenberg model, well, this is what we observe, right? So this is for exactly the same values of the disorder. So 4, 8, 12, 16, 20. So you see, this is like very large disorder as compared to the putative transition point from a couple of years ago. And all the different color shades, again, they're just different finite size numerics, right? So the light one is 8 sides and the darkest one, I do it on 12 sides. And so this looks at the relaxation rate as a function of distance from the boundary. And now I hope that it's clear to most people that, well, one, this is just already phenomenologically extremely different from the non-interacting model, right? There are huge finite size effects. If I keep changing the system size, actually at the boundary, this relaxation rate keeps increasing. That's one thing. Second, the relaxation rate nominally has increased by orders of magnitude, right? And second, well, if you look at these plots, I see actually not a single plot at a single disorder where I observe robust exponential decay of these Lioms. But I was just saying before, if there is no exponential decay of these Lioms like in the Anderson case, then you can never be stable to avalanches. And so this is the observation that at least up to numerical still, that at least up to disorder 20, there is no indication of any exponential localization of Lioms. And now what I want to sort of stress here is that still we have not explained things, but what is important is to realize that the localization length, so the critical localization length in the Anderson model, at what disorder does that happen? Well, that happens around disorder roughly 1.4, basically. So we're working here at disorders W, let's say pick the disorder 16 or 12 or whichever one you like, where in the Anderson model, the localization length is extremely small, much, much, much smaller than 1. So that means that if you now take any of these resonance arguments to sort of say that, well, to look in absence of rare regions, there's still going to be many body resonances that form. The probability of forming such many body resonances in the canonical sort of picture is extremely small, and there should be stability towards that. But at the same time, we observe that this relaxation rate has increased by orders of magnitude. So what is then the effect that increases this relaxation rate by orders of magnitude, right? And so I want to give you one, well, I'll try to give you two, depending on time, pictures of how one can understand why these integrals of motion actually keep growing and growing and growing. And so maybe, I mean, I saw Anatoli gave some sort of pedagogical lecture, so maybe he's explained this construction. So one thing we can do is basically imagine you have a probe site with very large disorder that you try to connect to some bath. And I want to make a Liom out of this probe site here. And of course, if I don't couple this probe site to this bath, well, then nothing happens, right? So there is a perfect Liom, which is basically sigma z on this side. Now I'm going to perturbatively weakly couple this site to this bath. And I'm going to try to construct the integral of motion in, let's say, to first order in epsilon. And one way to do it is to just ask, well, what does an integral of motion have to be? Well, it needs to satisfy that it commutes with the Hamiltonian, right? Then it's an integral of motion. So, but my Hamiltonian basically contains a term H naught, which is large because we're assuming that the disorder is asymptotically large. So W is very large as compared to the rest. So that basically means that I can split this H into H naught plus all the rest. And I can try to solve this algebraic equation by recursion, right? That is that I find the n+1 approximation of this Liom by solving this recursion relation, starting from the ansatz that at zeroth order, tau is basically sigma z. And well, we can do this. So then we do exactly the same thing. We try to recursively construct this integral of motion and then look at its residual relaxation rate, just like I described before, because this relaxation rate is the important quantity. And so now if we look as a function of the order in this expansion at different disorders, what happens is that basically we see that at any value of the disorder, initially there is exponential decay of this relaxation rate, which is good, right? That's what we're trying to get. That's what happens in the Anderson case. But at some point in the expansion, this expansion starts to diverge. So this is essentially, this generates an asymptotic series that is divergent, basically. But we can look at the lowest possible order in this expansion and just ask, well, what if we truncate this expansion at the best possible order? This is sometimes by some people referred to as superasymptotic series expansions. Then we ask, well, what is the minimal relaxation rate that we get? And lo and behold, this minimal relaxation rate is exponentially small in the disorder. So that's exactly what we observed numerically. Now you can, of course, argue that basically, yeah, but you're just constructing this recursively. And of course, this was inevitable that this was going to diverge. So one thing we can do is basically, we can use each of these taus that we generated as an operator in an operator expansion, and then simply numerically try to find which is variationally the best possible Liom that can be constructed if the only thing we're allowed to do is make linear combinations of these taus that we have. And it turns out these are the dotted lines in my plot over here that actually, even if you construct the best possible Lioms, in the subspace generated by this expansion, they will not exponentially decay anymore after this sort of crossover scale where the perturbation theory starts to diverge. So the point that I'm trying to make is that, yes, in this series, there is a divergence ultimately. Of course, every term in this series is finite, right? So in that sense, there is an asymptotic series where every contribution is finite. It's just that if n becomes larger, the terms start to grow. And why do these terms grow? Well, these terms grow because of a phenomena which some people might refer to as operator spreading. And so I'll come back to that in basically a second. And I'm going to skip this slide because it's probably sort of confusing. But so now the question is now what, right? Because I've given you some numerics that shows that there's very good indications that the only thing that happens is that the relaxation rate is exponentially small in a disorder. And I've given you some perturbative argument that that's actually what you expect from this Birkhoff perturbation theory. So now let me just quote sort of Arnold on this, is that in general, he says the divergence of a series in perturbation theory is usually related to the fact that we're looking for an object which does not exist. And if we try to fit a phenomena to a scheme which actually contradicts the essential features of the phenomena, then of course it's not surprising that this series diverges, right? So the question is this a pathology, this divergence, or is this actually telling us what the physics is? And of course, I'm biased and I think it's telling us what's really going on. And so one way to understand that it's telling us what's really going on is to do an entirely different calculation. That is to just ask, what if I compute the Fermi golden rule relaxation rate for a spin that I couple on the boundary to this, let's say, disordered systems? And of course, again, if we want to explain how MBL emerges out of the ergodic system, then I need a mechanism for this relaxation to become smaller and smaller and smaller. And on the ergodic side, I could perfectly use Fermi's golden rule. But what sets this Fermi golden rule relaxation rate? Well, this relaxation rate is simply set by the spectral function on the boundary. And if I have a disorder, if I have a spin with a large disorder W, it will just precess at a frequency omega, which is W, right? So I just have to ask, what is the spectral weight or the matrix element at which I can absorb this frequency omega? And that's just a boundary spectral function. So when omega is much larger than J, well, we know that on the ergodic side in a many-body system, this spectral function is universal. It has this universal functional form, which is just exponential in the frequency. And in one dimension, there is just a logarithmic correction, which I guess some people call Araki analyticity or something like that. So aside from this log, it's just an exponentially decaying a function. So now we can ask, well, if we want to absorb a frequency W, well, what is the rate? It's just the spectral function. So now I just want to say that what is the typical level spacing that we can get in a numerically in a many-body system? Well, typically for all the systems that we can do exact diagonalization on, the level spacing is, let's say, 10 to the minus 4, 10 to the minus 5. That's kind of the smallest regime that we can reach. So if I just look at the spectral, where is the spectral weight, which is the relaxation rate, 10 to the minus 5? Well, that's somewhere here. And then I go check what is the frequency at which this happens. You see, I'm getting some number which is on the order of 3, right? And so again, that's exactly where we observe all the finite size MBL, let's say, transitions or crossover. So again, you see that this is exactly the same prediction as the prediction you get from this divergence of this Birkhoff series, which is exactly the same as the numerical observation of the decay of Liams because of avalanches, right? So all of these are exactly the same thing. Okay, so I think this divergence in this asymptotic expansion and the fact that when you truncate it to the optimal order, you basically get an exponentially small relaxation, and that is the same thing as the Fermi golden rule relaxation, gives some indication from both the ergodic and non-ergodic side that this is really the physics that is going on, right? And I think I'm sort of running out of time if I'm timing it correctly. So I'm maybe gonna skip these slides, but I've given you this Birkhoff expansion to try to understand the construction of these Liams. But one of the final things I wanted to explain is basically we can view everything from what is called the Krylov subspace of the Liouvillean. And there is a very simple sort of argument that you can convince yourself of that, again, you cannot construct exponentially localized Liams if what people sometimes call the Lanczos coefficients of the Krylov dynamics grow as a function of n. But okay, if you want to know exactly what that is, just ask me a question about it later. I'll try to wrap up. And so I think here is the revised sort of picture, is that basically I would say what we have been observing is that there is a regime of fast thermalization, which say happens for weak disorder, say roughly smaller than 3 or something like that. And from, well, 3 is basically just the bandwidth of the local bandwidth of the XXZ model. Once we cross that, thermalization is inevitably exponentially slow because locally you cannot find states to resonate with. So you will need many body states to resonate with, which means that you will need a lot of virtual processes before this can happen. So you go to a regime of quasi-localization where basically the thermalization is slow, but at a finite rate. And I mean, we have a lot of indication by now that this is simply exponential and this can be explained. So then at some point, of course, there will be an avalanche transition where these Liams that you construct are so well localized that you get into the MBL phase. And from numerics, we can definitely conclude that this only happens when the disorder is significantly larger than 20. But I would say that at the end of the day, this disorder is probably extensive. What we know is that in this slow thermalization or everywhere, the relaxation rate is simply beyond any order in perturbation theory, because it's important, which is why I've written it like this, to realize that exponentially small in disorder is actually e to the 1 over the inverse of w, right? And that is the small parameter, right? The small parameter in your problem is the interaction divided by the disorder. So all these exponentially small relaxations are essential singularities in your small parameter. So it means you need to go beyond perturbation theory to see it. I call this false vacuum decay in this operator Krylov space. And then one final thing to note, of course, is that we can just, what is the largest possible timescale you could ever get in our universe? Well, I would say that's the Hubble expressed in Planck constants, which is, that number is dimensionless. It's 10 to the 60. So if we convert 10 to the 60, in which disorder we would need such that the relaxation, if it ever happens, right, is the same as that, well, that's disorder 40. So basically, by pushing the disorder even a little bit more, the question is, it's already kind of academic, but still, I would say observable and measurable. But if we push the lower bound for the critical disorder much more than 40, it's become a really academic, but well, albeit interesting question, but you will never observe it because the time scales are longer than the Planck, than Hubble expressed in Planck. Which is just to add that whoever wants to observe this experimentally is going to either have to measure things exponentially precisely or wait exponentially long. And yeah, with this, I leave it up for questions.
Questions?
I wanted to clarify a little bit when you were putting this idealized bath adjacent to collection of spins.
Right.
What was? I take it this was a continuum of spectrum. It didn't have a non-zero level spacing. Is that correct?
That is correct, but what I tried to stress, and again, I should have maybe made a slide to go through the math a little bit, is that the idea of coupling this bath is just a construction in the sense that I'm not actually computing what happens when you couple a bath and solving this Liouvillean. It turns out that if you do perturbation theory in the coupling between a Markovian bath, which means indeed since it's Markovian, it has continuous spectrum. But if you do perturbation theory in the coupling, you'll actually find that if you want to compute what is the shift in the relaxation rate of the slowest relaxing mode, so that is perturbatively compute the Markov gap of this process, that this becomes analytically, you can just work it out. You have to do degenerate perturbation theory, and you can prove that in perturbation theory, in the coupling, the slowest relaxing mode is in the sector that at zero coupling had zero frequency because that's exponentially degenerate. And so you work through this calculation, and then you'll basically find that the relaxation rate is simply given by the norm of the commutator of the Liom, that whatever Liom that you constructed with the boundary operators. So this relaxation rate at the end of the day is simply the norm of the commutator of a Liom with whatever boundary operator couples the system to the bath. And well, now you see that whether I assumed that this was a Markovian bath or not a Markovian bath doesn't really matter anymore because I'm literally just measuring the relevant quantity, which is the matrix element that gets induced by the Liom when I couple it to a bath. So that's to answer that question. But yes, the assumption.
All of that, but I just wanted to just point out that like one of the key aspects of the avalanche mechanism is that this thermal spot, this hot spot, will definitely thermalize some neighborhood.
Right.
And the width of that neighborhood is a function of the level spacing in that.
Right.
And so, at least naively, if you're assuming a zero level spacing, the associated neighborhood would be infinitely large. And
no,
so,
well, again,
yeah.
No.
Okay.
I understand your point, but that is not what is happening. Again, because okay, Wojciech has told me many times I should not explain this construction the way I'm explaining it, because again, this question, of course, comes up all the time, and I understand it's a valid concern. But the whole point is that at the end of the day, the relaxation rate that is computed, it has nothing to do with this bath anymore. There is no bath in this calculation. It simply computes. Take any operator that is take any operator that commutes with the Hamiltonian inside a finite region, right? So I have a finite MBL region. There is no rare region in this problem. The disorder is very big. You have an exponential set of operators that commute with the Hamiltonian, right? Now I can try to make linear combinations of those operators. They're all valid Lioms. Now I'm just going to ask, make the Liom that has the smallest possible commutator with the boundary of this chain. That sets the matrix element for whatever you would couple next if you were to make the chain bigger and bigger and bigger. This is the quantity that needs to decay exponentially to get stability to anything, to resonances or avalanches. This has to decay exponentially, and that's the quantity that is computed. But it turns out that this is equivalent to the relaxation rate of this Markov process if you couple an infinitely large bath on the boundary. So they turn out to be the same, but
Okay.
the construction in no sense uses the continuity of the energies of this bath.
Thank you.
You're welcome.
So you mentioned like stability to resonances at some point. I was wondering if you had like done that estimate, like at what kind of accessible system sizes, at what disorder would you expect to like no longer see any resonances in some like in like the XXZ model?
Numerically?
Yeah.
Yeah, this is a harder question. That honestly, I don't really know how to answer from the numerics because, of course, when the system is very large, the formation of local resonances and the stability to avalanches give you the same kind of scaling because it's given by the same ratio of matrix elements to energy denominators. So at the end, they happen at the same time, but specifically in the XXZ model, if we construct numerically what it is, oh, wait, I can give you a slightly better answer, which has nothing to do with the talk that I've given, which I guess we can discuss some other time offline. But there is another much better way to exactly probe resonances, and that is to look, which you know from Anatoli probably also well, is to look at this fidelity susceptibility. So it's basically to look at what happens if I take a system and locally I change the disorder by an infinitesimal amount. If you look at the susceptibility, then actually you can probe how many body resonances you have, because if you were to just be, let's say, in a product state, then the susceptibility is small. And if there is a many body resonance, but this resonance is rare, then you can actually see this perfectly from the statistics of this quantity. And so I have not talked about this now, and I think this sort of more fine-grained version of this susceptibility has not been published, but there is a clear indication that resonances in the XXZ model in systems that we can do ED on, right, stop existing around disorder roughly 10 to 20. And I can show you that numerics, and I think it's sort of very convincing. You can see it from the difference between the typical and the mean susceptibility, because one will always keep diverging because of many body resonances, and the other one keeps going down. So when they start to separate, you can probe the onset of absence of many body resonances. So I would say numerically, let's say somewhere around 10 to 20.
Okay, thanks.
Is there any other question? I hope there is no question from our online audience. Okay, then let's thank the speaker once again.
Yeah, I enjoyed the rest of the workshop, and I'm really bummed that I cannot be there. So hope to see some of you soon.
Yeah, thanks
Bye.
for your talk.